So you're building with AI, and large language models, they feel like actual magic, right? But that magic comes with a crazy high price tag and some serious lag time. So what if I told you the secret to fixing both of these problems isn't some new, more powerful model? What if it's just a smarter way of remembering things? Okay, look at this number, 90%. No, that's not a typo. With the right strategy, you can slash your costs for calling a large language model by up to 90%. I mean, that is an absolute game changer for pretty much any app out there. All right, so that leads to a pretty obvious question, right? If you can save that much money, why are so many AI apps still so ridiculously slow and expensive? Well, the answer really comes down to how we handle the most common, repetitive questions. Look, at the end of the day, every single time you call a powerful model like GPT-4o, you're running into two huge problems. First, every single token costs money. It just adds up. And second, all that number crunching takes time, and we feel that as lag or latency. And that is the core problem we've got to solve. Okay, so let's really dig into what this means for a business. Because let's be real, this isn't just some techie problem, right? This is a fundamental business issue. I mean, the argument for caching is just, it's a no-brainer. First off, the cost. Why on earth would you pay the LLM to answer, how do I reset my password, for the 1,000th time? Caching just gets rid of that completely. Then there's latency. Your user gets an answer in milliseconds, not waiting around for seconds, which, is everything for a good user experience. And finally, scalability. By taking the pressure off your super expensive models, you can serve way more users with the same hardware you already have. It's a triple win. All right, so it's settled. We need to cache. But hold on, it's not quite as simple as just flipping a switch. There are actually two really different ways to do this. You've got the simple way, and then you've got the smart way. Okay, think about it like this. Exact match caching is kind of like a super literal librarian. If you ask for a book with the exact title, character for character, they'll find it, no problem. But if you're off by just one word or even a comma, they'll just stare at you and say it doesn't exist. Now, semantic caching, that's the insightful librarian. You can just describe what you're looking for and they get your intent. They'll find you the right book even if you totally botch the title. So what's happening under the hood with exact match caching? It's pretty simple, actually. It takes the user's prompt word for word and creates this unique digital fingerprint. We call it a hash. And then it uses that hash as the key to store and find the answer. Yeah, the flow is super straightforward. A new prompt comes in, we create that hash. We look for that exact hash in our cache. If it's not there, that's what we call a cache miss. Then, and only then, do we go bug the LLM. We get the answer, and then we store it using that hash so we're ready for the next time someone asks the exact same thing. Simple, fast, done. But here's the Achilles heel, the fatal flaw. An extra space, a different capitalization, a simple typo. Any single character change creates a totally different hash, and the cache has no idea it's seen this question before. It thinks it's brand new. And that's why, in the real world, its effectiveness is, well, it's pretty limited. And this is where semantic caching swoops in to save the day. Instead of just hashing the raw text, it uses something called an embedding model to convert the meaning of the prompt into a big list of numbers. We call that a vector. And now it's not looking for an exact match. It's searching the cache for other questions that have a similar meaning, even if the words are completely different. Okay, so now we've got two awesome caching strategies in our toolkit. The simple old-school key value method and this new advanced vector-based method. So the next logical question is, how do we actually build this thing? Well, this is where a really powerful tool comes into the picture. So does this mean you need like a whole bunch of different systems? One database for your exact match cache, then a totally separate specialized vector database for your semantic cache, maybe another tool for conversation history? I mean, it sounds like it could get really complicated really fast. And yeah, this is what that mess looks like in the real world. You end up with this fragmented stack of 4, maybe 5 different specialized services, each one with its own cost, its own latency, its own maintenance headaches. Honestly, it's a nightmare for developers to manage. Yeah, there's a much simpler way to do this. And that's where the magic of Redis comes in. See, Redis isn't just a simple cache anymore. It's a true multi-model database. It can handle your classic key-value stuff for exact match caching, and it can do high-performance vector search for your semantic caching, all in the same engine at the same time. This just radically simplifies your whole architecture.
Okay, so we've got our strategy down, we've got our tool, we're ready to go, right? Well, not so fast. Implementing semantic caching isn't just a one-and-done thing. To really get the most out of it, you have to tune it. And that brings us to this really important trade-off between how much you save and how accurate you are.
And it all boils down to this one setting, the similarity threshold. This one little number is what determines how close in meaning two questions have to be to count as a match. Honestly, it is the single most important decision you're going to make when you're setting this whole thing up.
Think of it like casting a fishing net. A high threshold, let's say 95% similar, that's a really narrow net. You're only going to catch questions that are practically identical. This gives you maximum accuracy, but you're going to get fewer hits, which means fewer savings. Now, a low threshold, that's like casting a huge wide net. You're going to get a ton of hits and save a boatload of money, but you run the risk of catching totally unrelated questions and giving a flat-out wrong answer.
And look, this is definitely not a one-size-fits-all kind of deal. If you're building, say, a medical app, you need maximum safety, so you're going to crank that threshold way up high. But for general chatbot, you can probably find a sweet spot around 85% similarity for a really nice blend of savings and accuracy. The right number really depends entirely on your specific use case. All right, let's put all this together. It's time to build the ultimate production-ready blueprint that really gives us the best of both worlds: insane speed and smart personalization. Okay, this right here is the gold standard. Here's how it works. A new prompt comes in and gets a hit in our semantic cache, which gives us a generic answer. But at the exact same time, we go and fetch that specific user's context from Redis, things like their location or their role. Then we take both the generic answer and the user's personal context and feed it to a really fast, really cheap LLM with one simple instruction: personalize this. And that's it. And the results? They are absolutely stunning. This hybrid approach is up to 90% cheaper and 40% faster than making a full-blown call to an expensive model. But here's the kicker: you're still delivering a personalized, context-aware answer. It is the perfect blend of efficiency and quality. So all of this brings us back to one final thought. In today's AI world, building a smart AI, well, that's just table stakes. The real challenge, the thing that separates the winners from the losers, is building an AI that's also ruthlessly efficient. So the question is yours?